Yeah, so thank you very much for the introduction. Today I will talk about simulation of crowds, big crowds, and do that all in real time. Yeah, so I've been working 20 years as an associate professor at Utrecht University in the Netherlands. And we have done research on human behaviors, and we try to capture that, put it in a mathematical model. And now, today, I will present how we moved from this model to a plugin, and a plugin in Unreal Engine in particular. So first, I will demonstrate the capabilities of the plugin by going through some examples. Next, I will talk more about the theoretical foundation, so a bit of simulation theory and how we try to mimic real human behaviors and put it all in a model. Next, I will talk how we implemented it in an engine called TerraCrowds engine and how we have integrated it into Unreal Engine. Well, then I will show some demos and also show how we have set it up, so basically how we connected the plugin to some real-world examples. Then I will talk about how to scale it up from 100,000 real-time to 1 million real-time, if people want it. And we will finish with some conclusions and a Q&A. Okay. So this is the first example, Lyra example. It's a multi-layered example that one of our students created. Then we have a black shark, so it shows that it also works in big open environments with 100,000 real-time. Or another asset we downloaded, the modern city environment, again 100,000 real-time. This is an example of 25K real-time MetaHumans that we animate and visualize also in real time. I will discuss these examples later on. But first, more about the theory. So how can you create a framework that's actually flexible and tries to mimic human or maybe robotic movements? So what's inside the framework? So this is a picture I have taken a few years ago when Corona just had finished. It was a big Dutch event, the first open event after Corona, called Paaspop. And you see a big crowd. But looking at this crowd, it is really difficult to distill all the individual motions and behaviors. So we have done that differently. So this has led to a crowd simulation framework, which I will discuss in the first 15 minutes. So first, we think about how to represent the walkable environment such that the computer can do fast computations with it. So I will give lots of examples there. And next, given a certain goal of a character that you want to control, so since we control individual characters, how to decompose such a goal into actions such that for each action you know what the start and the goal in your environment is. And given a start and a goal, we try to connect it using an indicative route. So an indicative route indicates how a character globally wants to walk or move through an environment, connecting the start with the goal. Then iteratively, typically 10 times per second, we pick a point on this route and we try to follow it. Well, this gives us a velocity, so a certain direction, and speed in which the character is moving into. But it's not only for one character, it's for potentially thousands or hundreds of thousands of characters. So what we do is each character looks in its neighborhood, typically to its nearest 7 or 10 entities, and is going to update this velocity based on things that happen around this character. So collision avoidance is taken into account, or going with the flow, or walking in a certain formation, or trying to avoid dense, high-density situations. And finally, we have a velocity which is being fed into an animation engine. So I'll walk through these layers one by one. First, the representation of the environment. So you see that most game engines are using the Recast Detour library, which is open source, created by Mikko Monone. So this has really become the industry standard. You can download it, you can play with it. And it works in a few steps. So the first step is you're given a 3D environment. In the second picture, the environment is being voxelized on the GPU. And all the voxels that are sitting on top of an obstacle are kept. In the next phase, you see that in the third picture, a flood filling algorithm is applied. So you apply a seed to a voxel that hasn't been classified yet, and you basically use a seed growing algorithm to find pixels or voxels that are roughly on the same height. Then an algorithm is used to trace the boundaries of the polygon that's formed by these voxels. Well, this can yield non-convex, so complex polygons. So these are being decomposed into a set of convex ones, so that you can make easy computations with it. In the next phase, a navigation graph is extracted. So basically you put a vertex on each polygon and you place an edge that connects a vertex to another one, to a neighbor polygon, if the polygons are adjacent to each other. And in this way you create a navigation mesh. And navigation mesh is a combination of a surface representation, here in blue, plus a graph. And the graph is typically used for planning global path using an A-star algorithm that can compute the shortest path in the graph. Okay, so this is the basis that's often used and also used by Unreal Engine. But this method has many issues, especially if you want to deal with huge environments. So we have been working on digital twins of thousands of square kilometers, and you cannot use recast for these purposes. Also, it has lots of issues with narrow passages to get characters through, because it's a voxelized environment. So it is discretized. Also, it has issues with difficult geometry, like if you have a stair and it has different step heights. So this method has also many parameters to deal with these issues. So sometimes it takes a lot of time to calibrate all these parameters to get the right output. So we have been working on other techniques, so exact techniques, to compute in an exact way a representation that can be used as a navigation mesh. But such an exact technique where we are using exact number types are very expensive. So even in this very simple house case, we computed a multi-layered environment, but it took like 8 seconds to compute and it consumed 1 gigabyte of memory. So suppose you have a huge game world, it's not going to work, it's not going to scale. So we had to develop other techniques that were fast, but still exact or precise, I have to say. In my opinion, an ideal navigation mesh has to satisfy these criteria. It has perfect coverage, meaning that if there is a place where a character can stand, then this location should also be represented in a data structure that goes with the navigation mesh. In addition, it has perfect connectivity, so if there is a path in the game world that connects a start with a goal, then this path also should be able to be retrieved via the data structure. It should be computed efficiently, implemented robustly, and it should require little storage, so that it also can be used on machines with constrained memories. And it also allows for fast pathfinding queries, so hundreds of thousands in real time. Okay, so this has led to this data structure. So as input, we are given, in this case, it's a planar environment, so an environment that just sits in 2D. It is created by a set of vertices that describe obstacles, in this case a bounding box, plus a footprint of polygons. Now, based on this information, there are libraries, also open libraries, like a Boost library, that can compute a Voronoi diagram or a medial axis of the environment. And this is basically a graph that has edges, and these edges are furthest away from obstacles. And this allows you to do all kinds of nice mathematical operations. It gives you a graph that represents all motions that can be made. And we annotate this graph with information, so we subdivide the environment into a set of non-overlapping cells, so that each reachable point actually is represented by the data structure. So in mathematical terms or computer science terms, when the environment is defined in n vertices, it can be stored in order n memory, so it's just linear, and it can be constructed in n log n time, which is really fast. And this structure is really nice because you only have to compute one navigation mesh that can be queried by characters with a various radius, so you only have to have one mesh. You can compute like the points on this medial axis, which allows you to do distance operations very cheaply. And distance operations is like a basic operation you need in crowd simulations a lot to determine what's the distance to obstacles, what's the distance to other things. And you get it for free, basically. This structure also allows you to compute a corridor that can be like a set of corridors, real corridors, in a building like this one, but it also can be like a set of streets. So it defines a blob of free space through which characters can move. And this structure allows you to compute a set of paths that can be the shortest path for a point or a shortest path for a disk. So basically, characters with an arbitrary radius. It also gives you all kinds of operations that are very fast to compute, like computing visibility, computing mutual visibility for disks, etc. And this structure can also be extended to multi-layered environments. So like a planar environment can have a triangulated irregular network, so basically a height mesh. And we can concatenate these height meshes to form a multi-layered environment. And all these properties I just said, so like computing visibility, computing shortest path for disks, can also be done in the same time in these multi-layered environments. And that's good. You can also update such a navigation mesh in real time, even when there are 100,000 characters using the mesh. And in this way, characters don't get stuck, which is good. Okay. So this is a bit about representation of the environment. The next phase is that we can compute a set of start and goal positions to answer queries. So we are given a certain goal and we want to solve that. Well, we have created some tools for that. Later I will talk about that. But this is maybe also nice to show. It was a paper that just got accepted by a student of mine, Nizar. And there we applied a large language model to each individual agent. And what we do is each individual agent has a persona, so which means that a firefighter will react differently than an agent, than an officer, a police officer, for instance. They can observe the environment, they know the types of obstacles there are, they can observe other people when they're in groups or not. And based on the perception, they can put things in their memory. When the local or short-term memory is full, they abstract the ideas into a long-term memory. Based on things that happen during the simulation or when people are talking to each other, memory, perception, etc. can be changed, and even persona can change. This can also change the planning, so all the agents do a 24-hour planning, they break it up in hourly plannings and then into smaller plannings, and that lead to actions, so basically queries or commands to our engine saying you're now here, you want to go there and make sure you get there, and then collision avoidance is being taken care of, etc. And the interesting thing is that this leads to way less of setting up environments than you have to do in code. So for instance, there was a truck and food was being offered, and one NPC discovered that the food was free of charge. So he started communicating to other agents like, hey, this is free, come on, let's grab something. And so you saw a communication wave starting to appear, but at a certain moment the food was gone. And then you saw a communication wave going back, people getting angry and then resuming their journeys again. So I think this is quite interesting to see. So in this case, we used ChatGPT 4.0, and now we are trying out other models that also can run locally. But I think it's an interesting way to model crowds, especially in when you are modeling synthetic single environments with a pattern of life, for instance. Okay. So what comes out from these models is a start and a goal location for each agent. Okay, in the next phase, we are connecting the start and the goal. We can use our data structure, the Explicit Corridor Map, for that. It computes a blob of free space. Inside this free space, we compute, for instance, a shortest path that has some amount of minimum distance or clearance to obstacles. Or we can compute a path that is at the right-hand side. And what we do is iteratively, typically 10 times per second, because also humans have like internally an update rate of 10 hertz. They doing the following. So for instance, I want to get out of this room. I'm looking at a door, and I'm going to do a step in that direction. And that's also what I try to mimic with this picture of a kid. There is a trail of raisins, and the kid is actually moving to the next raisin, picking it up, putting it in his mouth, and continuing. So this is also what people are doing internally. So we compute a preferred route inside a blob of free space, and that gives you all kinds of nice opportunities to do path planning. And you are flexible enough to deviate from this route, and that's the reason why you are not taking a route and moving on the route, but we need the flexibility to diverse from this indicative route, because that's the flexibility you need when you're doing crowd simulations. So this works when you have a single character. What happens when you have a crowd? So lots of research is being done also in our research lab. There is a motion capture studio, and we do all kinds of scenarios. So for instance, these are two of my former PhD students. They are standing in a certain position, and we are asking them swap positions. And you can repeat it many times. And in this way, we can discover the variables that are important when you're doing collision avoidance. And in this case, it turned out that people are moving a bit more slowly, or so they are accelerating or decelerating, or they are slightly rotating their bodies. And with these experiments, you can discover the statistical distributions that go with these parameters, not only in this situation, but also when you have two females or other types of elements. And we put that in a mathematical model. And like 10 years ago, we applied that in a game situation. We were back then very happy because there were no collisions. And that was one of the first times that such a model appeared. However, this is not realistic because there is no variation in speed. There are no group motions. People are not colliding, while in reality they are colliding. There are no social groups, etc., etc. But at least this was a basis where we started. Okay, so we did follow-up research. This was a colleague of mine, Sibren Stuvel, now working for the Blender Foundation. And we studied how people are actually making their way through a dense crowd. And we can take that into account as a parameter, how quickly you can actually move or push through a crowd, which is important. Also, we studied how we can interpolate between individual behavior. So this is, for instance, a person who is looking at their mobile phone and really pushing through the crowd like this. While other people who are maybe more social, they're actually going with the flow. And a certain moment, there is a big difference between the real direction and the preferred direction, and then a person starts pushing through the crowd. And for each individual, we can set this parameter, how individual he or she is, or how collective they are moving. And in this way, you can merge individual motions with big crowds where people go with the flow. It's a very simple trick, but it worked. Okay, so there are internally like 12 levels, because you also need to have some levels that do some updates of the navigation mesh or do group planning, etc. But these are the main levels. Well, if you want to read more about these levels and about the intrinsics, about the pseudocode, you can download these PhD theses. You can easily find them online when you're looking for these names and then type in PhD. And then you can read the background of the engine itself. Okay. So let's talk about, so this is more the theoretical framework. Well, at a certain moment, we have converted this framework into algorithms. And the question is how to achieve high performance. Okay, so we call this engine the TerraCrowds engine. And actually, it was a whole journey to scale up the entity count. I believe it was like 7 or 8 years ago when we created at least we tried to create a plugin for the Unity engine. And we were able to simulate, visualize, and animate 2,000 agents in real time. And we were bottlenecked by the animations because we all did it on the CPU. And having more than 2K skeletal animations is quite expensive, as you can know. But this was not a real problem. because we use an object-oriented approach. And so you have an object that stores all properties of an NPC, like position, X, Y, Z, velocity, animation state, plus like 50 or 60 more properties that we are needing to have a full-blown, well, set of behaviors. This was not working because of all kinds of memory constraints. So we decided to throw away everything, and we switched on creating an entity component system, so a data-oriented approach, which was way better. So we could simulate like 75K in real time, which was already way better. But then we thought like, well, there are many bugs and memory overflow bugs, so we should change that. And we want to have very efficient algorithms that all run in parallel. So we switched from C++ to Rust. And in this case, we gained 25% out of the box in performance, which was good. So we reached 100K real time. But then it was really difficult to push it even further. And by doing lots of profiler sessions, we noticed that it was really constrained by memory. So, so we switched from using a data-oriented approach to a memory-oriented approach. So what we do there is that we put memory and memory transfer central in the data structures and the algorithms. And in this way, we went from 100K to 500K real time. By using many tricks that are also performed when you're doing GPU programming. So we made cache-aware algorithms. We made thread local algorithms. So when you have many threads running in parallel, each thread has its own memory, and we try to keep it contained as much as possible. Sometimes you have to communicate, but you have to do it really deliberately. Also memory reusage, etc. When you want to go from 500K to 5 million, that's also possible, but then you need to do other kind of tricks. And at the end of the talk, I will talk about these tricks. So you see that each time you are 10xing, you have to use maybe different ways of thinking. And so that was a whole journey we went through to get it done. So this is an example. We took our TerraCrowds engine. It's written in Rust. We compiled it to WebAssembly in this case, with a JavaScript layer on top of it. And in this example, we put it in Unity. And this transition also allowed Unity to make a multi-threaded compilation in the browser. So we could have 200K NPCs in real time in a browser. And that shows basically the power of the engine. The performance of WebAssembly is roughly half of the performance of a native application natively compiled to, for instance, Windows or Linux. So this tells you something about the performance of the engine. Okay, but now the step to Unreal. So we have created some design principles. We want to integrate it one-on-one with the Unreal editor. So you can access all the low-level API functions if you want to program everything. So you can even create your own collision avoidance method, your own method to compute a global path, or just use our method. You can inject it with agents from Mass or use our system. So you can blend it with many systems of the Unreal Engine. So next to an API, we created some blueprints, but also more a high-level crowd logic approach. So you can model with areas, and these areas can be combined to create basically activity routes. So people are spawned in a certain area, then are moving to hit a certain other point, move again to another point, and then maybe exit the scene. And now we are also adding other types of building blocks like queuing, unordered queuing, one-way directions, areas where people are assembling. And with these building blocks, you can way more easily model big crowds. For the animation and visualization, you can also determine as a user what system to use, based, for instance, on the distance to your camera. So nearby, you can, for instance, select 5 fully fledged MetaHumans, and then maybe at a further distance, skeletal-based humans. And then we have like 3 or 4 levels of distance LODs for vertex-based animations, and then even characters that are further away, you can use imposters or other things. So you can select your own systems. You can select ours that we have created, but also the ones that are present in Unreal. Then the navigation mesh, because we really think there is an advantage of using these exact navigation mesh, especially in multi-layered environments with stairs or in huge open environments. So we have created a library that offers you high-speed Boolean geometry operations. So basically, you start with a plane, you can cut out holes, you can combine objects, and this way you can model or author your walkable environment. That can be a planar environment or even a multi-layered environment. And with that, we can compute a navigation mesh. So in this example, we added a tree and the navigation mesh is updated directly. And the good thing about this nav mesh is you don't need to bake it. There are no parameters involved because it's just an exact computation. Okay. Some integration into the Unreal editor. There are many, many parameters you can work with. So what we have designed is that you can create character profiles. And a character profile is a set of parameters and methods you can choose that are applied to create certain behaviors. You can override it with your own behaviors. And then with each parameter, well, that's a variable, you can also select a statistical distribution. For instance, for the walking speed, in Europe, for instance, people are walking with 1.2 meters per second with a certain standard deviation. And when you are spawning agents, then you are using these distributions to draw parameters from these collections of distributions. And this way you can create a diverse set of humans. Okay. Next to blueprints, we started with controlling each individual agent with blueprints, but this was not fast. We could simulate maybe 5K or 10K in real time. So this is not going to work because you're treating the blueprints as a programming language that does actually do object-oriented programming. It's not going to work if you want performance. So you need to do it in a data-oriented approach where you're working with collections of buffers and you're doing mass operations on data sets, basically. And in this way, you can easily go to 100K or more. Also, we put all this logic on separate threads, otherwise you get stalls. It's not going to work. For the visualization animation, so again, you can select the method based on camera distance, and based on the fidelity you want, and also the speed you want. And this way you can compose your crowds. Here are some performance tricks. It was important to run everything asynchronously, and in order to do that, we had to create multiple buffers so that there were no waitings involved when, for instance, the graphics card wanted to have access to the data. Again, the blueprints had to be created in such a way that it applies to as many people as possible. We completely separated the simulation and the visualization and animation to not have stalls. So you easily can have simulations at 4K, 60 Hz. That's easily reachable with this framework, and that's also what Unreal Engine wants. And yeah, you can choose to use our optimized renderer or not. That's up to you. So some demos and how we did it. So this is a demo we already created 1 year ago with some older technology, but it shows like the process. We used the city sample project and we made sure we simulated 25K in real time. When we had 100K MetaHumans, then we had a very low 4 Hertz frame rate, and that's not acceptable, obviously. What we did, we extracted the footprint from the buildings and we built a nav mesh on top of that. We programmed the crowds directly in C++, since 1 year ago we didn't have the blueprints ready yet. So this took way more time, obviously. And we used 3 LODs for animation. So for characters very close to the camera, we used the cinematic setting of the MetaHumans. And for the rest, we used a simple vertex-based animation where we did a simple blending between people standing still or actually moving, but it was quite simple. So there's an example. You see still some strange movements because we didn't interpolate correctly. In the current version, that works way better. But it was the first approach to making it happen. So this is something my student worked on in a few days. He downloaded the Lyra example. It's a multi-layered example. And in this case, he extracted the polygons or the nav mesh created by the Unreal Engine, and he converted it with our API into a multi-layered navigation mesh in our format. And he used that to set up a scenario. For that, we designed some simple markers you could place in the environment that says, like, here should characters be spawned, then it should go there, and then there, etc. And we programmed that in blueprints. And that resulted in a simulation like this. Here we used Unreal's animation system. So it shows characters can walk in a multi-layered environment, so to show that worked. Okay, so this is another example where we show that you can do 100K in real time on an 8-core computer with a 2070 GTX card. So it's a pretty fancy computer, I would say. So what we did was there were blueprints that were nested, and we extracted the buildings and trees and obstacles you would collide with. And we put that in our API, and then in this way we extracted the walkable environments. That's done fully automatically. And the good thing is that when you are making modifications in the editor, the nav mesh is being updated within a millisecond or so. You can do it interactively. In this case, also the motions were being programmed with blueprints, and we used 3 LEDs for animation visualization. So there's an example. It's recorded in the editor, so sometimes it blinks. We try to resolve that right now. In the release, you don't see these blinks. It shows 100K in real time at, I think this was 90 Hertz 4K. Okay, so another example of Black Shark. We took their API. It's a very nice API they've created to extract features in your environment. So you can say, like, I want to have the data layer of all buildings or all trees or water or whatever. And you can feed that into our API to create a navigation mesh. And this example, we we imported the data, we did all the queries, and we created the nav mesh all within 2 seconds. So that was pretty fast. And then we set up a crowd with just very simple blueprints, and then it was being visualized. So here it's an example of 100K entities moving in this vast open space. Also, this runs at 60 Hertz 4K. Okay. So now the question is how to scale it up from 100K to 1 million. So this was a project we did 3 years ago for a company, CAE, with many other companies. And they wanted to have a digital twin of the city of London, 1,500 square kilometers of photogrammetry data with a pattern of life of 1 million people. So basically, you could zoom in a certain area, zoom in a building, and an apartment, and then maybe there are a family living there with 2 kids and 2 parents, and maybe they are bringing the kids to school, they're going to work, etc. So at that level, from a statistical point of view, it was being modeled to have a realistic distribution of people. And so we modeled certain scenarios where you had like soldiers from the US Army, who were being submerged in VR, and they had to evacuate 100,000 people from the city center. So this was the first approach. We could simulate 1 million in real time in a cloud. However, we only were able to visualize like 50K or so back then. But this was already 3 years ago. We also did another project for AWS. We helped creating a SimSpace Weaver. So when you want to have this big amount of people, you need to have like a spatial OS, so a program that distributes the people in the cloud among different virtual machines. So we made an implementation for Hadean, the Mega Spatial OS, but also for AWS SimSpace Weaver. On the right-hand side, we had a simulation running in the cloud. It was running at 10 hertz. And we made an implementation in Niagara that could animate and visualize 1 million in real time. So how to scale it up? What people typically do is they decompose the environment into non-overlapping cells. In certain cases, they can be square, like in the AWS case. But in the more optimized case by Hadean, they have like a 3D composition of the space. And also the cells can merge when it is not very crowded, and they can split up when it is very crowded. So it's dynamic. So the Hadean case is way more efficient than the AWS case. So it's being split up in cells. These cells have overlapping boundaries. And when an agent or a character is in a boundary, some partial information is being sent to the other cell so that the other cell can do proper collision avoidance and other things. And we got it to work. Then we worked on an improvement of Niagara because that system copied way too many instances of the buffer, so we had to change it in order to handle 1 million real time. Also, there were some memory constraints because there was too much information that needed to be sent to the graphics card. So when you want to simulate 1 million people that are who are all individuals, then 10 gigabit of information was being generated per second, which is way too much, obviously. So we needed to do lots of data compression and also spatial compression, like people who or characters that are very far away from the camera. We are only updating them, being sent over from the network to a local machine, like once per second or so. And with these compression techniques, you can have 1 million visible entities at 90 hertz, 4K in real time. So it's doable. Okay, conclusion. So I've talked about the crowd simulation framework, lots of psychology research, lots of motion capture research. And we have seen that from a technical point of view, it's most difficult to integrate all these components such that they are compatible, it works together, and that it is still performant. Well, performance can be gained by having a memory-oriented approach, which is being addressed in an API that's data-oriented. And it should also be treated data in a data-oriented way in order to keep this performance. And we have seen that using blueprints really helps in the ease of access to such an API. Well, if you're interested in trying out this plugin, we can put you on a list. We try to release this as soon as possible. So we are now trying it out to some clients. But we officially hope to release it in Q4 when it is on the store. But in the meantime, we can give some people access to already play with it so that we can get feedback, and you can do that for free. And I'm happy to take questions.